Okay, welcome Ralph and Jordan and Victor and Bradley and Jesus. We'll start more about matrices, which is most of what this class is about, or a lot of what the class is about. Let me share my screen and we'll go over the plan for the day. Okay, the plan today is, as usual, I'll start out with any questions you might have. And then after that, and we're going to see this a lot, is TFAE. So if you remember, last time we had TFAE, and do you remember how many items we had on TFAE? Yeah, just two. So today we're going to add another one. And I wouldn't say every day we're going to add another one, but we're going to add a lot of them. So we're going to have another TFAE item. And then after that, I'm going to review a bit from last time. It's been a while. I hope you all had a good long weekend. If you were hoping for that wonderful powder for skiing, we didn't get it. But we still got to have a weekend at least. So I'm going to review what that cofactor matrix was. I'm not sure if y'all remember cofactor matrices, but they're going to come up again today. So I figure I better review. Today's kind of a light day in terms of stuff to do. So, I can take questions and go over examples and stuff like that. And then we're going to talk about another way of finding the inverse of a matrix. So we've already learned one way of finding the inverse of a matrix, which was to basically adjoin the matrix with the identity, RREF, and the right-hand side is the inverse. We learned another way of finding the inverse, if you remember, and that is to very carefully RREF one at a time, and very carefully RREF, and then look at the elementary matrices that you use to make that RREF happen, and then take the inverse of those elementary matrices in reverse, and that gives you the inverse also. But we're going to have another way of finding the inverse. Inverse is pretty important, and that is using the cofactor matrix. And we'll see how that works. Okay, and then what we're going to do, and this is something we're not going to do too much in this class, but today we're definitely going to do it, and it does come up in a big way next quarter. And that is, we're going to be looking at matrices where the elements are not numbers. So we're going to look at matrices where the entries of the matrix are functions. And how do you deal with inverses and determinants and things like that when you have a matrix whose elements or whose entries are functions and not just numbers? And that comes up in a big way next quarter in differential equations. And you need it. And in particular, I'm going to do this, even though the book doesn't do it, it's the whole point. And I want to do what the whole point of this piece of section is, and that is the Wronskian. And I don't expect any of you to know what that word means, but you will have seen it by the end, and it's not that hard. That's the good news. So we'll talk about the Wronskian matrix for a vector of functions. And next quarter, you'll use that to decide on things. But I figure I might as well, the book, it's weird. The book goes over matrices with function entries, but it actually doesn't talk about the whole point. So I'm doing it even though the book doesn't. And the whole point is Wronskian. And it doesn't add anything harder, by the way. So I'm not, throwing some evil stuff at you. But it is because I kind of made a promise, and I'm breaking my promise in that you don't need to know calculus for this class, except that because I'm adding this piece in, you need to know calculus. So you need to know how to take a derivative, and it'll be easy, I promise. So that's going to be the Wronskian. And then we're going to get into polynomial interpolation. And we're going to do only the easy style today. And that is that if, let's say you have 5 points in the xy plane, and you want to find the 4th degree polynomial that goes through those 5 points. Okay, well, it turns out you could do that with a matrix. And well, I'll show you how to do that. I won't do it with a fourth degree polynomial because that's a 5x5 matrices and those are no fun. You can use a computer for that though. And I probably will use a computer for some of this today because I want you to get used to it. I mean, that's called the real world. And it is important to know how to use technology. You know, don't think that in your career you'll never use technology because you're fooling yourself. You definitely need technology. In fact, I was watching. I start my morning every morning with a lecture, and I'm doing it's a Caltech lecture series on astrophysics and astronomy. And at the end, there's a Q&A time, and they asked, "What is it you all need to know?" Every one of them said, "We all need to know how to computer program to do astrophysics." So it happens. So you have to know how to at least use a computer, and programming is a good thing too. So I'll probably use, Symbol Lab since it's already programmed for us, because I can't expect you to know how to code things, but I can expect you to know how to plug into Symbol Lab, and we'll play around with that. What I'm not going to get into, which would be a number 8, but I'm not doing it. And that is, what if you had 20 points and you wanted to say, what is the quadratic that goes through it and one doesn't go through? And you want to say, what's the best quadratic? And we will do that later. And that is probably the biggest and most important application there is in terms of today's job stuff, but not right now. So that is the plan of the day. Again, hopefully you had a nice long weekend. Weekend's coming. I want to ask you something. And again, don't feel, and this is not being recorded, if you put it in the chat box. And don't, you could go either way. I don't really, it's up to you. I want to find out. If I had a review for the final and maybe the second exam in person, with social distancing in a large room so you can sit far away from each other, would you come on campus at LTCC?
If I'm in the area, then I would for sure, but I might be gone for a lot of this quarter.
Yeah. It's definitely not, it won't be a requirement. And what I'm thinking about is if I get enough people that would come, I'd do it. And then I would ask to see if there's anyone that's good with technology, and maybe you could live stream it on YouTube and record while I'm doing it. That's what my thought. So those who couldn't do it could at least watch on YouTube. But I'm thinking about it. But I don't. If no one would come, then I'm not going to push it, because I'm going to have to push it. I'm going to have to fight with the administration and say, hey, this is really safe because there's only 9 people in the class. We can get a big classroom, and we can make sure social distancing happens and all that. I just think it would be worth it, and I'm willing to do it. Okay, and I will be vaccinated by then. That's the good news. Okay, yeah, probably the same time as the lecture. Probably same time as the lecture. I don't have a date yet. I can't guarantee it yet, because again, I have to get permission. It'll probably have to go to the board. I mean, that's how big this would be. But it's worth it. I'm into fighting for you guys and fighting for, making sure that you can get that little support. Okay, and it wouldn't be for a while. So we're talking, over a month from now, month and a half or something. Okay, so I just wanted to ask you. So it sounds like I have a critical mass that would come, and those who wouldn't, hopefully, at least it'd be recorded. And even if you couldn't go live stream, you could still watch it later on YouTube. So the information will still be there. Okay, so anyway, I was just thinking about it. Okay, so are there any questions that you might have about anything?
Yeah, I have a quick one. Do you have practice exams like you did in Calc for these exams?
Uh-huh.
Oh, cool.
In fact, I think I haven't looked recently. I'm gonna spend some. I was gonna do it last weekend, and then something happened. I'm probably gonna do it this weekend to take a look and make sure it's about right in terms of content and stuff. I think there's a link to it now on the syllabus.
Cool.
Yeah. So because I had them last time I taught it, and I'm not changing. I mean, I know we're online now, but the content doesn't change at all. So the practice test should still work. So the answer is yes. And I purposely don't put a key up there, because then it's not a practice test. Then it's just problems to do. Do you see the difference? So people always complain that there's no key, but that's the whole point. The whole point is that you You're practicing a test, and there will not be a key when you take the regular exam, by the way. I am not going to give you the answers. Yeah, question?
I'm sorry, I couldn't hear you earlier. Where would the practice tests be?
I believe, I haven't checked recently, but let me reshare. Let me go to that one. Then I can show you. That's the easiest. Unfortunately, we're in Word, so I have to move on to internet. And if I go there and home, I haven't looked at it yet, so no guarantee, but it will be there eventually if it isn't there, but I think it is. And if we scroll a bit, see where it says exam 1?
Okay.
If you click that, yeah. And a Word document just pulled up. Do you see?
Yeah.
So it's not really, is it online? Yes, is a downloadable file, which is not the same thing as like a Canvas online, but do you really care that much? As long as you can click it. Yeah, so they're up there, the practice tests. I haven't looked at them in a while, so I have to glance at it, make sure that they're still relevant, but I'm sure they are. Again, content, that's one great thing about teaching math. Math doesn't change. Technology changes a little bit, but matrices have not changed since I was born. So that's the good news, is that once it's up there and it should work. Okay, let me go back. Okay, other questions? Homework was easy? Okay, there's no questions. We might even finish early, but I always say that. We never do. You never know. Let me talk about the big theorem of the entire course. We're going to be revisiting throughout the course, and that is TFE. And what it says is TFE. Remember what TFE stands for?
The following are equivalent.
Right, the following equivalent. And what that means is if one is true, they're all true. And if one of them is false, they're all false. So as long as you know one's right, then they're all right. And that makes them equivalent. So 1 and 2 is what we got last time or last week. And that was number 1 is A is invertible. And number 2 was that if you take the RREF, reduced row echelon form of A, you get the identity. And then number 3, and this is often the easiest one to show, is that the determinant of A is non-zero. So if the determinant of A is 0, then if you tried to find an inverse, what would happen?
You won't.
Exactly, you won't. That's what TFE means. Okay? Whereas if the determinant of A is not equal to 0, if it's say 4.3, then if you tried to find the inverse and you were, good at it, then you'll find it. It's doable. There is an inverse. Okay, so that's a biggie. And determinants, it may not feel like it, but determinants are a lot easier. It's a lot easier to find a determinant than it is to find an inverse. Do you agree?
I would say so.
Especially for a 2 by 2. You just glance at it. AD minus BC, you're done. Okay. And even 3 by 3 takes a little work, but inverses are much harder. So number 3 is the most useful when you're checking to see if there's an inverse. And that's all you care about. Unfortunately, sometimes you actually want to find the inverse. Is the determinant enough to find the inverse?
No.
No. But we're going to see today that it's a big step, actually. That it's going to be part of the inverse, but that's going to happen a little bit later, is that we're going to have, and not much later, we're going to have another way of finding the inverse, and that's going to involve the determinant. And if the determinant is 0, then you can't do it. But if the determinant is non-zero, you can. All right, so how do you prove something like this? And we've already proven TFE for 1 and 2. How do we add something in? What do we have to do logically to show that they're equivalent? If you already know 1 is equivalent to 2, what do we have to show to prove that 1, 2, and 3 are all equivalent?
You have to show that 3 is equivalent to at least one of them.
Exactly. And you could choose whichever one is easier for you is the one you should do. Does that make sense? So you could either RREF and get the identity, or you can find it's invertible. Either way, if you know the term is non-zero and you can get 1 or 2, that's good enough. And you have to go the other way. You have to start at 1 or 2 and end up with a non-zero determinant. Any questions on that? All right, turns out the proof is pretty easy. And the key on the proof, so now I'll pop it in, is something we did last time. Do you remember last time that you can take a matrix A and you can write it as E1 times E2 times ... times EK times RREF of A? Do you remember we were able to do that? I know, 5 days, long time.
What does the E stand for?
E stood for elementary. So it means that you could write it as a product of elementary matrices times RREF of A. We did that last time. Do you remember vaguely at least doing that, all of you?
We did that to find a determinant, right?
Yeah, that's how we found the determinant. But the point is we did it, so I don't have to redo it because we already showed that.
Yeah.
Is that clear? Yeah, so we did that to find the determinant, but turns out I'm going to be doing it for the proof too. All right, so now what I can do is I can say, well, I've rewritten A. You can always do this, right? And again, in this class, if you even talk about the word invertible, that means A is square. So I'm not saying it. I'm not going to mention that it's square. It's just clear. Is that okay with everyone? Okay, I'm not going to mention it's a matrix. If I use capital A, it's a matrix in this class. Okay, so I want to find the determinant of A. So what I can do is I can take the determinant of both sides, right? And that's the classic math thing, right? Right, the do unto the left as thou must do unto the right, the golden rule of mathematics. So I can take the determinant of both sides. And I know the determinant of A is going to be the determinant of E1 times E2 times ... times EK times RREF of A. Everyone okay with what I just did? Nothing too fancy, right? Okay, now I use a really important property that we talked about last time. And that is, if you have the determinant of a product, what can we do?
You can break it apart and make it determinant of E1 times the determinant of E2 and so on and so forth.
Exactly. So I can write determinant of E1 times the determinant of E2. And what's nice is now I'm working with numbers because the determinant of a matrix is a number, it's not a matrix. Times ... times the determinant of EK times a determinant of RREF of A. Any questions on that? I forgot the equal sign. There we go. All right, now we got to look at this and it's time to analyze it. Do you remember what the determinant of an elementary matrix was? Not always the same thing, but what were the possibilities? I'll just write determinant of E. Whoa. Did weird things with that, parentheses E with Microsoft Word. Okay. So if you have an elementary matrices, there are three things. What are the three kinds of elementary matrices? Or the three kinds of row operations is another way of looking at it.
You swap
Switching
rows.
rows.
Okay, now if you switch rows, what's the determinant?
It's just one.
Not one. Good try though.
-1.
It was -1. Do you remember that? So if you switch rows, the determinant is -1. So it's either -1. Okay. What's another thing you can do for what's another row operation?
Multiply by a scalar.
Right. Now, if it's a multiplication, not any scalar, a non-zero scalar, and that's really important. So if you multiply by a non-zero scalar, then what is the determinant of that?
1 over that.
No, it's multiplied by the scalar. The determinant.
Yeah, it's just that number. It's just that number. So I'm going to call that number K. Sound good? K being a non-zero number. Do you remember that theorem? Again, this is all last time, but last time was 5 days ago, so it's easy to forget. Okay, or what's the third row operation?
Add another row, the multiple of another row.
Yeah, so you replace a row with that plus a multiple of another row. And what is the effect or what is the determinant of the elementary matrix that does that?
There's no effect.
Right, but what is the determinant of that matrix? Of the
1.
element? It's 1. Any questions on that? All right, so that tells us that what we're looking at is the determinant of E1 times the determinant of E2 times ... times the determinant of EK. Well, these determinants are never zero. They're either -1, some non-zero constant, or they're 1. So let's write that down. So therefore, and let's copy and paste this part. The determinant of the product of the elementary matrix part is non-zero. Because if you multiply a bunch of -1s, non-zero constants, and 1s, you can never get 0. Right? Basic math. Any questions on that? And it's non-zero. How about C? I'm just giving a letter for C being a non-zero constant. So because of that, what I can now say is the determinant of A is equal to C, some non-zero constant C, times determinant of RREF of A. Anyone lost on that? Okay, so I took that horrible messy part and basically I got rid of it. That was the whole point of this. Okay, but if you have a square matrix and you RREF that square matrix, what could happen?
You could get I.
Yeah, you can get the identity, or what else could happen? If you don't get the identity, so notice first thing, if REF of A is equal to I, then the determinant of the RREF of A, what's the determinant of I?
1.
Is equal to 1. And in particular is not 0. Any questions on that? Okay, so we're almost there. Okay, so that's one thing that could happen, is that if you and you get I when A is invertible. We had that as a theorem. Remember that? Or it's right there. That's TFE. Okay, so that's what I needed for that part. Now we got to go the other way. Okay, so what else could RREF of A be? If not, then what do you know about RREF of A?
It's unique.
For a square matrix, if it's not the identity, what do you know about the last row? Yeah, it's a row of zeros, but not any row. The last row must be zeros. Does that make sense? Then has its last row all zero. So if the last row is all zero, what do we know about the determinant?
It's 0.
Yeah. Therefore, the determinant of A is equal to 0. And vice versa, by the way. Goes both ways. So that's the proof of TFEE number 3. Either you have determinant 0, and therefore RREF of A is not the identity, or you have the determinant of A is non-zero, and therefore RREF of A is the identity, because those are the only two choices. Any questions on the proof of this? Okay, again, this is a big theorem. I'm not proving every item in this class that we do, but I figure TFAE is the biggie, so I try to prove that one at least. And so as we go through and we add more, I'm always going to prove those guys. We're not going to prove everything else. In fact, I think I won't prove the next theorem. I think you guys would probably like either log off or tune out if I proved everything that we ever did in this class. But I do want to prove something so you get used to proofs. Any questions at all on this proof? Okay, and again, you definitely want to have this down, this TFAE, because that is the most important theorem, because we're not done yet in this class. Pretty much every time we talk about something, we're going to have something to add in TFE. So we've talked about determinants, and we added that one in. Any questions so far? Okay, now it's time for a little review. And that is what we did on Friday. Do you remember the cofactor? So believe it or not, I just copied and pasted from the lecture notes from Friday. And let me do this. And that is if A is a square matrix, the ijth cofactor of A is the matrix. Cofactor of A, ij, is equal to -1 to the I plus j times the minor of Aij. Do you remember what the minor of a matrix is? The ij.
The entry at the point.
What's that?
The entry at the ij position.
That's what Aij would be, but if we want the minor of Aij, do you know what that is? That's where you erase the ith row, and you erase the ith row and erase the jth column. Do you remember that? And you get a new matrix. Then instead of n by n, it's n minus 1 by n minus 1. Remember doing that? And you take the determinant of that. So that happened on Friday. And again, 5 days is a long time, but that was what we did on Friday. But I figured, I better remind you of that, because I was guessing that some of you probably forgot. All right. Maybe not. Maybe, you got it. All right. So let's do a little review. Let's see if we can find the cofactor. Here's a matrix: 1, 0, 4, 1, 1, 6, 3, 0, 10. Okay, I just kind of made up a matrix. Then I'm going to do some. I'm going to let you do the rest of them, because I want to make sure you can do this, because this is important for today. And if I want the 1, 1 component of the minor matrix, I'm going to take -1 to the 1 plus 1. Those are the two ones. It's the 1, 1, so 1 plus 1. And then I'm going to take the first row and first column out. I'm going to erase those or cancel them. And I'm left with this matrix 1, 6, 0, 10. 1, 6, 0, 10. Okay, so stop me if you're not following something, because I want to make sure that y'all getting this. Then I take the determinant of this 2 by 2, and my recommendation is memorize that. So it's 1 times 10 minus 6 times 0. Okay, good. AB minus CD. Okay, and negative 1 to the 1 plus 1 is 1, right? Negative 1 squared is 1. 1 times 10 is 10, minus 6 times 0 is 10 minus 0, and that's 10. Any questions on that? Okay, then I'm going to do the 1, 2. So now I'm going to take negative 1 to the 1 plus 2. Now I'm going to take that first row and erase the first row. And take the second column and erase the second column. And what I'm left with is 1, 6, 3, 10. So I'm looking at the matrix 1, 6, 3, 10. Then I calculate that. What's negative 1 to the 1 plus 2?
Negative 1.
Negative 1.
Yeah, it's negative 1 because 1 plus 2 is odd. That's all you need to know is odd even. So that's negative 1. And then I take 1 times 10 is 10 minus 6 times 3. What's 10 minus 18?
Negative 8.
Negative 8. So I take negative 1 times negative 8, and I get 8. Any questions on finding the minor, at least for those two positions? All right. So what I'm going to do is I'm going to assign you the next positions. Okay. And I want you to work out one of these because it's good for you to practice. So I'm just going to go in order of what I see on my screen at least. All right. So I just did 1, 1 and 1, 2. Bradley, I'll let you do 1, 3. And then Jordan, I'll let you do 2, 1. Victor, you do 2, 2. Jacob, you do 2, 3. Caesar, you do 3, 1. And Ralph, you do 3, 2. And Jesus, you do 3, 3. I was like, perfect. We got just the right number of people. I actually didn't know how many people are going to show up, but I got it right. And put it in the chat box when you get it. Don't just put your number because you got to remind everyone which one you were doing. So go A, like, 1, 3, for example, equals. In your chat box. Okay, I'm going to type out. Hopefully y'all got it right. I'm seeing a couple. Okay, so let me go find them. A13 is negative 3. Just a minute. It takes forever with Zoom up here to get to that matrix. Just a minute. There we go. So we got A13 was equal to negative 3. We had A32 was negative 2. And A21 was 3. And what else do we have in here? No, A21 was 0. You changed your mind on it. That sounds better anyway. Okay. A23 is 0 with a question mark, so let me double check. So, so second row, third column. So second row, third column is that one. You get rid of that and that. Yeah, you do get 0. That was A23. And zeros can happen. A23 is -2. And then A33 is 1. Four, 5. Let's see, and there should be another one in there. A22 is -2. And A31 is -4. All right, I want to stop and make sure, is there any questions on any of these? Any questions? Can I do A23? And I didn't check the work, by the way, so let's check the work. Okay, so if I do A23, let me just copy and paste one of these and change everything I need to change. A23. Well, that's going to be -1 to the 2 plus 3. And then if I take the second row and third column out, so that's gone and that's gone. So a second row, third column. I'm a little worried about A23 actually also. Yeah, so let's look at this. Okay, so let's plug in what we get. And if you get rid of the second row, third column, we have a 1. Then we have a 0. And then we have a 3 and a 0. And if I take the determinant of 1, 0, 3, 0, I get 0. So let's fix that. Yeah, and by the way, it's a good lesson is that there's a lot of arithmetic to do. And if you make one mistake, you get the whole thing wrong in what we're about to do. So beware. So I did a couple of them, you all did the rest, and hopefully you all got the rest of them right. So again, you can check each other's work and hopefully it all worked. All right, so in particular, I can now write down, I can look at these cofactors and say, now I have a cofactor for each entry. So now I do the main thing. We look at the matrix, the cofactor matrix. In fact, let's write that down up here. The cofactor matrix of A is going to be, so let me write A first and then we'll change the numbers. So if you look at the 1, 1, that's a 10. 1, 2 was an 8. And then 1, 3 was -3. 3, 2 is -2. What's wrong one? 3, 2. Third row, second column, -2. And 2, 1, second row, first column was a 0. And 2, 3 is a 0. So that's second row, third column is a 0. 3, 3 is a 1. 2, 2 was a -2. 3, 1 was a -4. Any questions on the cofactor matrix? Okay, it turns out this is not the matrix that we're going to want. But the good news is the matrix that we want, you don't have to do too much more. And let me give you the big definition of the one we want. That is and the book gives two different names. The book tells adjugate or classical adjoint. Maybe because I'm old, I learned the classical name. I always called it the adjoint. So when I learned it, I learned it as the adjoint matrix of A. And the adjoint matrix of A is just the transpose of the cofactor matrix. Any questions in this definition? Any questions on that? So transposes are pretty easy. Let me double check and look at the chat just a second. Yeah, good. All right, so I'm hoping you all know how to take a transpose. So that just reflects it basically across the diagonal. Or another way is you read the rows and write columns. And in fact, the first time I ever taught this class, one of my students had no eyesight, was completely blind. So I really had to say, am I reading rows? Am I reading columns? So if I read 10, 8, -3, 0, -2, 0, -4, 2, -2, 1, if all you did is heard me say it, you don't know whether I'm talking about A or A transpose. So if I read it as rows, then I'm talking about this cofactor matrix. And if I read it as columns, if I switch, then I'm talking about the adjoint. So the letters we use, in fact, what I'm going to do, if we want to find the adjoint of this matrix that we started with, I think that's the same one. Yeah. 104, 116, 3, 0, 10. Then we can say the adjoint of A is equal to the transpose of this matrix. So the 0 and the 8 switch. So that's an 8 now, and that's a 0. The -3 and the -4 switch. So that 4 becomes a 3, the 3 becomes a 4. The -2 and the 0 switch. 0 and -2. Any questions on finding the adjoint of the matrix A? Any questions? Okay, so you might look at this and say, what's the point? All right, I found this matrix, but why do I care? Right? And I want you to do something just for fun. And maybe I'll do it in my head to make sure. Yeah, okay. Just want to make sure we didn't make any mistakes. Okay, what I want you to do is I want you to multiply these two matrices in either direction, either A times the adjoint of A or adjoint of A times A. Just do that. So get a piece of paper out and multiply those two matrices. Tell me what you get. So just explore. Take A times the adjoint of A. And you'll get a matrix, see what you get. And you'll have to maybe type in the 9 numbers and with commas in between or something, because it's hard to put a matrix in a chat box. But I want to give you a minute to multiply those 2 matrices and get a new matrix. And you should all get the same thing. Although some of you might do adjoint of A times A, that's fine. And the hint is you'll still get the same thing. So I'll give you a minute or two. Shouldn't take too long. It's not like we have fractions or anything. -2 top left and bottom right. All right, I'm a little worried about your A22. I mean your A adjoint 22. So right in the middle. Okay, so I see -2 along the diagonal, but what about off diagonal? What do you get? Yeah, 0. Okay, so if you're all able to do it, and you can still do it if you're still working on it. You should get that matrix. So hopefully you all got that matrix. Did y'all any questions on that? When you multiplied A times the adjoint of A, or adjoint of A times A, it turns out. You'll get the same either way. That's the first question. The second question I have for you is, what is the determinant of A? See if you can find the determinant.
8. 8.
Not what the determinant of A times the adjoint of A. What's the determinant of A? That you got to do some work. And the hint is expand on the second column. Is so much easier than anything else. Because you got those zeros on the column. And Jesus says -2. Let's see if other people agree. Okay, I'm seeing some agreement. So let me do it. We're going to have, let me write it as an equation. So we're going to have a -1 to the 2 plus 2. Okay, notice when I expand on the second column, I don't worry about the first and the third entry. All that matters is this one little guy right there. So it's -1 to the 2 plus 2 times 1. I'm just using the determinant formula, times the determinant of the minor. And that's 1, 4, 3, 10. So times the determinant of 1, 4, 3, 10. Let me get there. And if you do that, we get, well, negative 1 to the 2 plus 2. 2 plus 2 is 4. That's even. So that's just 1. 1 times 1 is 1. So that really doesn't matter. So it's just the determinant of this matrix. And that's 1 times 10 minus 3 times 4, which is negative 2. Do you notice anything coincidental? Hopefully you do. From these two things we just tried.
It's negative 2 times the identity matrix.
Exactly. It's negative 2 times the identity. So now the big theorem. Now I'm not going to prove the full theorem. I could. It's just a little messy. I like to do it by exploration, and then you're probably convinced, especially since I'm telling you it's true and it's in the book too. But here's the big theorem. And it says that A times the adjoint of A is equal to adjoint of A times A, which is equal to the determinant of A times the identity. Isn't that beautiful? So that's always true. And again, that could be proven. You just kind of be very careful with your AIJs and the definition of multiplication, and you'll end up getting that. So you can trust me, hopefully. Any questions on this big theorem? Okay, it turns out there's a corollary to the theorem that's even more important than the theorem itself. And that is, what happens if you divide by the determinant of A on both sides? Or all three sides if you want. What do we get on the right?
Wouldn't it just be A?
On the right-hand side, if you divide by the determinant of A, you get I, right? Because we have determinant of A times I. If you divide that by the determinant of A, you just have I left over. But that tells us, in particular, that if we divide by the determinant of A, then A times 1 over the determinant of A times the adjoint of A is the identity. So now the big corollary. The corollary is that if A is invertible, okay, and that's the same thing as saying if the determinant is non-zero, then A inverse is 1 over the determinant times the adjoint of A. Any questions on that? And that's a main theorem. So what this does is this gives us a third way of finding the inverse of a matrix. And depending on what you're doing, sometimes the first way is the easiest, sometimes the second way, sometimes the third way is the easiest. So this gives us another way of finding the inverse. Inverses are very important. For example, if you ever want to solve a system of equations, you need the inverse to solve it, okay, to do it with the matrix way. And that's how we can do it. Any questions at all on this example? Okay, not this example, it's corollary. Okay, so the good news is we can do an example, and I'm just going to do the example we already did. So I don't want to spend all the time, calculating. But let's see if we can find the inverse, A inverse, if A is this matrix that we started with, 1, 0, 4, 0, 1, 1, 1, 6, 3, 0, 10. And the answer is we've done all the work. So what we can do is we can use the fact that the adjoint of A was this guy, and the determinant was -2. So we know that's true. And we also know that the determinant of A was equal to -2. So now very easily, we can find this inverse. So to find the inverse, what do I have to do?
Multiply each entry by 1 over -2.
Yep.
-1/2.
Right. So I just multiply each entry by -1/2. So let's do that. And whoops, not one, that one, that one. So let's copy and paste this guy and then adjust. So we can say, instead of adjoint of A, now we can say A inverse is equal to negative 1/2 times this matrix, which is equal to, and remember, multiplying a matrix by a constant multiplies all the entries by that constant. So the 10 becomes a 5, the 0 stays a 0, -4 becomes -2, 8 becomes a 4, -2 becomes a 1, the other -2 also becomes, oops, let's try again. The other -2 also becomes a 1. I forgot to change signs too. We're doing negative 1/2. So 0, 2. And then we have -4. And then +1, +1. And then we're going to have +3/2. 0 and -1/2. And that's our inverse. Any questions on finding the inverse of this matrix? Okay, you'll notice this is very different than the other two methods. I mean, adjoining it with the identity and RREFing feels nothing like this, does it? Okay, I mean, it doesn't even look anything like this, but you get the same answer. Any questions at all on this particular example? Okay, so now we're at the point where we have 3 different ways of finding an inverse, depending on, which is easiest to use. Okay, now let's move on. And let's see if you can use the adjoint formula. This will be a lot easier, even though there's no numbers. Sounds harder. For the general 2x2 matrix ABCD. Let's see if you can find it. Let's see if you can do it. I'm going to give you, shouldn't take more than 2 minutes. Probably not more than 1 minute if you remember how to do it. See if you can do it, the adjoint formula to find the inverse of the general 2x2 matrix. And I kind of, last week, had told you, good to memorize it, but we'll actually prove that it works. So let's see if you can do that. Give you a minute or two, and let's see if you can do that. And let me know when you got it. The nice thing is the adjoint is easy. Not sure? Okay, give you another 1 minute and then I'll do it. Because it's pretty quick. You got it, Jesus? Good, good. And it should look just like what I told you is a good idea to memorize. And it should be pretty quick. All right, let's work on it quickly. So the first thing is I want to find the cofactor matrix. And the cofactor matrix, let's look at it and make that happen. What I'm going to do is I'm going to start with the matrix, and I'm going to say, well, what is the determinant of the minor? Well, when you take the determinant of a minor, for example, with a 1 by 1, you're just left with D. Is that clear? If you get rid of the first row and the first column, all you have is D. So the determinant of a number is just the number. Any questions on that so far? Okay. And -1, by the way, to the 1 plus 1 is just 1. So it really is just D. And then if we do this B, and we take the cofactor of that, then you get rid of this row and this column, and you're left with C. Then over here, if we get rid of the C's row and column, you're left with B. And if you get rid of D's row and column, you're left with A. Oops. But then notice for this guy, -1 to the 1 plus 0 is -1. So that's a negative C. And similarly, -1 to the 2 plus 1 is also -1. And this was, sorry, 1 plus 2. And here, -1 to the 2 plus 2 is 1. Any questions on that? So there's our cofactor matrix. How do we find the adjoint? Very easy.
Transpose.
Yeah, we take the transpose. So that means we switch the B and the C. That becomes a C. This guy becomes a B. Any questions on that? And then finally, if we want the inverse, the big theorem said that A inverse is 1 over the determinant times the adjoint. So let's do that. So what we can say is that A inverse is equal to 1 over, and the determinant of this matrix is AD minus BC. Times the adjoint. And if you want, you can put that together. I'll let you do that if you feel like it, or you can leave it like this. You can write it as D over AD minus BC, negative B over AD minus BC, C over AD minus BC, A over AD minus BC. But most people write it the way I've written it. Any questions at all on using this adjoint formula to find the determinant of a general 2 by 2? Not too bad? Okay. So when we look at this A, B, C, and D, for example, in your head, what do you think A represents?
A number.
Okay, so in your head, you feel like A represents a number. Okay, by the way, real or complex?
For now, real.
Yeah, real.
Okay. It turns out it can represent whatever you want it to represent. Okay, so let me give you an example that's going to look really different than any of the examples we've done so far. So let's say A was the function matrix t squared 3, 1 minus t. Is that a matrix?
Yes.
Yeah, it's a matrix, but it's not a matrix whose entries are just numbers. It's a matrix whose entries are functions. Any questions on that? Okay, but the good news is we know how to find the inverse of this. So if we're given a matrix like this, then we could find the inverse if it exists. If it doesn't exist, you can't find it, right? So how do you find the inverse of this matrix? Let me give you a minute to see if you can find it. Did you guys find it? Okay, so what you do is use the adjoint formula, which I've already proven with A, B, C, D. And you can think of these as A, B, C, and D. So we take the determinant of A, which is t times 1 minus t, and then minus 3t squared. So that's t minus t squared minus 3t squared, which is t minus 4t squared. Everyone following that? Or is that too much in my head at once of the algebra? So we take 1 over the determinant, which was, again, t minus 4t squared. And then we times the adjoint. And the adjoint says we're going to be switching the A and D. So the t becomes a 1 minus t. And the 1 minus t becomes a t. And then we're supposed to make these guys negative from the adjoint formula. Any questions on that? Okay, does this always exist?
No. It
No,
could be
when?
t equals 0.
Yeah, t equals 0 is bad, and that's not the only time. Forgot to write inverse. So this is for t not equal 0. T not equal to, just a minute. And what else can't it be?
T can't be 1/4.
Yeah, t can't be 1/4 because you factor out a t, then you get 1 minus 4t. So it's not 0 and it's not 1/4. Ooh. Okay, because if it's 0 and 1/4, if it's 0 or 1/4, the determinant doesn't exist. I mean, the determinant is 0, so the inverse doesn't exist. But if t is not 0 and it's not 1/4, then this inverse exists. Any questions at all on this example? Okay, when have you seen this before?
Vectors,
What about vectors, though?
parametric
Parametric.
equations, stuff like that.
Not really parametric. And remember? Here's a hint. It starts with a J.
Jacobians.
In Jacobians. So remember, you had Jacobians, and Jacobians were matrices of functions. Do you remember that? They weren't just numbers. When you took the Jacobian, you got a bunch of functions in here. And if the Jacobian is 0, if the determinant of the Jacobian, so the Jacobian is 0, then all kinds of things go wrong. Do you remember? Did Bruce talk about that? Nobody remembers?
Yes.
He did talk about it? Yeah, the Jacobian cannot have determinant 0. If the Jacobian has determinant 0, then the transformation doesn't work. So the Jacobian must have non-zero determinant. Okay, which means that the inverse has to exist. Any questions on that? So one application of these non-constant matrices is when you're dealing with double and triple integrals, because those matrices that you get from the Jacobian are going to be non-constant matrices. They're going to be matrices of functions. Any questions on that?
I have a question for you.
Sure.
On the adjoint of A, why are the -3 and the -t² negative? Shouldn't they become positive when you take the transpose, like when you have the cofactor of A?
Well, remember you do -1 to the I plus j?
Yeah. And then I got negatives for those entries.
Right. Now, transpose doesn't change the sign. It's just transpose only changes placement.
Got it.
So that's the reason is transpose, it doesn't do that.
Okay.
What it does is you read the rows, turn them into columns, you read the columns, turn them into rows. There's no multiplying by -1 or anything. So that makes sense?
Yeah. Do you know what it is I'm thinking of?
I'm not sure. I'm not a good mind reader, sorry.
That's all right. Thank you.
Especially on Zoom. Huh? Yeah, so it's hard to know what you're thinking of, but this is how you do it. So it turns out only the off diagonals change signs, whereas the on diagonals change places for 2 by 2. Okay. Now let me give you a definition. It's not in the book, but it's kind of the whole point of doing this, getting ready for next quarter. And this is the following. Let's suppose you have functions, f of x, g of x, and h of x. And let's suppose there are twice differentiable functions. Okay, and by the way, sometimes you'll let the variable be t instead of x. The letter doesn't matter. Okay, and let v be the vector f of x, comma, g of x, comma, h of x. Then the Wronskian matrix is a matrix with rows v, v prime, and v double prime. Any questions on the definition? Okay, this is going to be a little tough for me. And that is, it's hard to convince you that this is important. But I will promise you that if you can't do this next quarter, you're going to get at least one problem wrong on an exam. Because you're going to be dealing with the Wronskian, and you're going to be using the Wronskian to decide whether you have a solution, a full solution of a differential equation. And all I can tell you is believe me. Can you believe me? Since I do teach differential equations opposite years. Bruce is teaching next quarter. I taught last quarter. Last year. Okay, so this is the Wronskian. Okay, so let's see if you understand the definition or not. And that is, see if you can find the Wronskian for the functions f of x equals e to the x, g of x equals e to the x, f of x is e to the 2x, g of x is e to the x, and h of x is the function 4. Let's see if you can find the Wronskian for this example. Let's see if you can do it, and then I'll do it too. So it's not a trick question or anything. But it is, like I said, it's really important next quarter, so I figured I should show it to you. It's one of the main points of this class. And this is the one time you actually have to remember calculus, basic calculus.
I think I've got it.
Okay.
So the first row is going to be, wait, are we supposed to tell you when we?
Give another 30 seconds. Give another 30 seconds. Let everyone else finish too. And then we'll do it. And in fact, why don't I get it ready with the insert symbol stuff. Equation. And get a bracket. Matrix. 3 by 3. Ah, shoot. I always do that. I got to be in the matrix to make it happen. There we go. Okay, so what is the first row? That's supposed to be really easy. You don't need
to the 2x.
Yeah, e to the 2x.
E to the x and 4.
E to the x. And 4. Okay, what's the second row?
2e to the 2x.
So a little harder, but not too hard. And then?
E to the x and 0.
Yep. E to the x. Good. You remember your derivatives? And 0. And what is the third row?
4e to the 2x. E to the x and 0.
Good. Any questions on that? Okay, so now what I want you to do is I want you to do 2 things. So I want you to do one thing actually, is prove or disprove that the inverse of this Wronskian always exists for all x, sorry. See if you can do that. Hint, TFAE.
The determinant can't ever equal 0.
Right. So what'd you get for the determinant? So what is the determinant? It's pretty easy, actually.
I'm still doing it right now, but I can tell that it's a multiple of exponents, like exponentials with e to the x involved. So it can't equal 0 in that case.
Did you get negative 8e to the 3x?
Yes.
Yeah, so if you did this right, then you should get negative 8e to the 3x. Again, you always look at it when you want to find a determinant and say, do it the easy way. And the easy way is the third column. Do you agree? Go for those zeros. Okay, notice that this 4 is in the 1, 3 position. 1 plus 3 is 4, is even. So that means you don't get a negative. So you just get 4 times the determinant of this 2 by 2 bottom left matrix. Well, that determinant is 2e to the 3x minus 4e to the 3x, which is negative 2e to the 3x. Negative 2 times 4 is negative 8. And negative 8 e to the 3x is always non-zero. That you should know from algebra, actually. Intermediate algebra, but still algebra. So therefore, by TFAE, always cite the theorem you're using. The inverse of the Wronskian exists for all x. Any questions on that? Okay, you're going to learn next quarter. That means that these 3 can be a solution, can be the solution, the sum of the constants times these 3, or I can use the words that we have in our class now, the linear combination of these 3 functions is the solution to a differential equation of second order. Now, I don't expect you to know why that's true or anything like that, but Bruce will tell you why and prove it. For now, you can believe me that that's going to happen. So you're going to be doing this kind of work next quarter to show that functions make the full solution of a differential equation. Any questions on this example? Any questions? Okay, the last interesting little point is another example, and that is find the quadratic polynomial that goes through the points 1, 4, negative 1, 6, 2, 9. Okay, so I have 3 points. And can you all see that these don't lie in a line? If you look at the slope of the first 2 points, you get negative 1, I guess. If you look at the slope of points 2 and 3, you get 3 halves. No, you get 1. So you get different slopes if you look at different pairs of points. And that means they don't lie along a line. And any 3 points that don't lie in a line lie in a unique parabola. Do you remember that from algebra? So now the question is, how do you find that particular parabola? Any questions on that idea? What do you think we have to do?
Put these points into a matrix of some sort.
That'll happen, but not the first step. We have to do some more stuff first. All right, let me ask.
Find the equations for the line.
We don't want a line, we want a parabola. So definitely not equations of a line, because that's not what we're doing. All right, so let me ask you a question. This is kind of the big hint. What is the general equation of a parabola? Y equals what?
X squared.
X squared.
No, that's not general. That's a specific one. And this is definitely not y equals x squared, by the way. Negative 1 squared is not 6. In fact, none of these squared.
Ax squared plus bx minus plus c.
Much better. Okay, that's the general equation. So let's write that out. Let me put it in math form. So we can say y is equal to ax squared plus bx plus c. Okay. And by the way, more generally, sometimes you'll say that y is equal to, you kind of read it in reverse. So often you'll say y equals a naught plus a1x plus a2x squared. Do you agree that's the same thing? Why did I say it in that messy, ugly way? What is that leading you to? Any thoughts? Okay, the reason I said it that way is that if you had, instead of a fitting parabola, let's say you had 20 points, and let's say you had 30 points, okay, and you didn't speak Chinese. I'll tell you why in a minute. So you had 30 points, and you don't speak Chinese or Japanese, and you want to find the best fitting 29th degree polynomial. Then in that case, you need to list your letters, not A, B, C, because you'll run out. If you speak Chinese, you never run out, it seems like. But you write it as A1, A2, A3 until you get to A29. Does that make some sense? So in the more real world being how you use this stuff, you typically have very high degree polynomials and you don't use A, B, and C. So I want to give you that little warning. Okay, so what I'm going to do now is I am going to change this slightly just to mess with you. Do you agree I didn't do anything by writing equals y instead of y equals? Y'all good with it? Okay, the reason will come up next. So now let's plug in. So let's plug in our points. If we plug in 1, 4, then I get A plus B plus C is equal to 4. Do you agree? All good with that? Plugging in 1, 4? Okay, what do you get if you plug in -1, 6? Make sure you understood the first one. We'll find out.
A minus B plus C equals 6.
Good. A minus B. Again, it wasn't a trick question. Plus C is equal to 6. And what do you get if you plug in 2, 9?
4A plus 2B plus C equals 9.
Good. Any questions on that? Okay, now you should look at it and you say, this looks like our class now, doesn't it? Why does this look like our class?
We have a system of equations.
Yep.
We can turn it into a matrix.
Exactly. We can turn this into a matrix equation. So let's turn this into a matrix equation as follows. And I think it's easy if I copy and paste one of the other matrices. How about one of the 3x3s? There we go. So we could take the matrix. Now we're going to have a 1, 1, 1. We're going to have a 1, -1, 1. And then we're going to have a 4. Then we're going to have a 2. And we're going to have a 1. And then we're going to have times the matrix. Let's do that. Nope, can't do it that way. Just a minute. That way. Times the matrix ABC is equal to the matrix 4, 6, 9. Any questions? Okay, so notice I turned a question that didn't look anything like a matrix equation, did it? Find a polynomial, quadratic polynomial through 3 points. And all of a sudden, it's looking like linear algebra, isn't it? How do I solve a times x equals b?
We need to find the inverse of our 3 by 3 matrix.
Exactly. I need to find the inverse of the 3 by 3 matrix. 1, 1, 1, 1, negative 1, 1. Let me write this down. 1, 1, 1, 1, negative 1, 1, 4, 2, 1. And let's do that. And I'm going to do that the easier way. What's the easier way? The easiest way. All right, no one's telling me. As soon as I tell you, you're going to say yes. And that is use a computer. So I'm going to go to Symbol Lab. And what I want is the inverse. And I got to move my Zoom stuff out so I can actually grab stuff. I'm going to go see all and inverse. Then I'm going to get a matrix. I want a 3 by 3 matrix. And it was 1, 1, 1. And then 1, negative 1, 1. And then 4, 2, 1. And hit go. And it liked it. Some fractions, but since I use a computer, computers don't complain too much. Okay, and I get negative a half, 1 6, 1/3. We get a half, negative a half, 0, 1, a third, negative a third. Any questions on using a computer? Was that easy?
Yes, very easy.
Yeah. And I'm telling you, this is what I'm trying to say. Don't do every problem by hand. Learn how to do it by hand and then use a computer. Otherwise, you're going to waste your time. You're going to hate this class because we're going to have a lot of problems where you want to use a computer throughout this course because it's much faster. So now what I can do is I can say that, let's just do that. There we go. Then now ABC is going to be the inverse matrix, which was negative a half. One sixth. And one, oh, I lost it. Just a minute. 1/3. And then the second row was a half, negative a half, 0. And the third row was 1, 1/3, negative a third. Double check. Any questions on that? Now it's easy. So let's see what we get. So what do you get for the first entry, the top entry? So you got to multiply these two. Not that hard. What do you get for the top entry? 2. Good. What do you get for the middle entry? Good, -1. And what do you get for the bottom entry? Bottom entry, +3, that's better. Okay. Any questions on this so far? Okay, now we can take this and we can write down our answer. So now we go back to the original way of writing the equation, which remember, y is equal to ax squared plus bx plus c. So now we can say y is equal to, we have ax squared, so 2x squared. And then we have minus bx, or plus bx, which is minus x. And then plus 3. How do you check your work the easiest way?
You just plug in.
Yeah, plug in. If I plug in 1, I get 2 minus 1 plus 3, and that is 4. If I plug in -1, I get 2 plus 1 plus 3, and that is 6. And if I plug in 2, I get 8 minus 2 plus 3, and that's 9. So it actually worked. So checking your work is really easy. Okay, by the way, just a note, what if I added a 4th point? And actually, let's add some more points. I'll just throw some more points in. What would happen?
We add more. We add more rows.
Yeah, you're going to end up with a matrix that is 6 rows and 3 columns. Now, can that be an invertible?
No.
Never. Okay. And if the points are somewhat random, it's always no solution. Do you believe me? All right.
Yeah.
So, question?
Because if they're random, then they don't fit any sort of like pattern, so they can't be a.
Right. If they're somewhat random, then you're never going to get a solution. So the bigger question is not find the quadratic polynomial through the points, but what is the best fitting quadratic polynomial? Okay. And can that be done with linear algebra?
Probably.
The answer is definitely. Okay. And it's not just definitely, but we need some more weeks before we can get there. So it's hard, and it can be done, but it's pretty messy. And do you think it's useful to do that kind of stuff?
Yeah.
Yeah. And if you can get really good at it, especially on a computer, and someone offers you $100,000 for a year for work, what do you tell them?
Yes.
Definitely no.
No.
No, because you can get $250,000.
Oh.
So that's a no, because they're cheaping you out. Just let you know that there's a huge field. Artificial intelligence is all about that. It's all about best fitting. It's all about coming up with the best fitting quadratic or cubic or whatever, and deciding the degree actually is really hard. Okay, that's deep, and I can't even get close to explaining it. But if you can do all that, boy, that's like the #1 job that people are skill that people are looking for right now in AI, is to be able to handle that kind of stuff and how it's used and why. And I'll just tell you, that's just how it works. Facial recognition, it's all about that. You're finding best fitting curves for the pixels that you're given when you take a picture of somebody. Does that make sense? And you do that using this stuff. Okay, more advanced than what we're doing today. But we're going to get to not the full level of what you do making that huge money, but a big piece of it. So let you know, this isn't just find a polynomial. It's kind of fun. It's actually huge piece of industry that's very well sought out right now, that all AI uses it. So big deal. Any questions on this? Any questions?
Would you also be able to use this to find the projectile motion of a moving object that's moving parabolically?
Yeah, but actually in the real world, it's never going to be perfect, right? You always forget that air resistance does exist. I think you know that, right? So what you're going to do is you're going to find the best fitting parabola. Does that make sense? And it won't be perfect. And so it's the more advanced piece that, so into the real world, it's not going to be perfectly parabolic. Does that make sense? And this is exactly what you would do, okay, using a computer. Any questions on this idea? Okay, we have 3 minutes left, which isn't a long time. Maybe I'll look at the homework just to make sure that you don't think I'm cheating you.
So for right now, if we encounter a problem like this, it's going to end up being a square system of equations.
Yeah, it's going to be perfect for this week. That's going to change later in this class. So I just wanted to get you ready for what's coming up later. Okay, so I got to go up a lot. I think I went too far. Just a note, we're skipping chapter 4 because I'm assuming you already know vectors in Rn because you already learned about vectors last quarter. Okay, and third quarter, by the way, which is a prereq. So you'll notice if you look at the questions, use a formula for the inverse in terms of cofactor matrix to find the inverse of this guy. Does that look kind of like what we just did? Okay, here, look at this A. Does there exist a value T for which the matrix fails to have an inverse? What do you think you do to that, to decide?
Take the determinant.
Exactly, take the determinant and see if you ever get 0. Then you have to look at algebra at that point. Any questions on that? Okay, so I just want to go through. Let me go some of the beginning ones. For the following matrix, determine if they're invertible. If so, use a formula of the inverse in terms of cofactor matrix. Think you'll be able to do something like that? So look like what we've been doing? Hopefully. So I wanted to kind of give you a heads up of what's coming. And that's what we're doing. Okay, find the inverse of this matrix. Okay, and again, take a determinant, multiply by the adjoint, and that gives you the inverse. Okay, so all of these are that kind of thing. Any questions on what to expect coming up for the homework? Okay, and to let you know, again, we're skipping most of chapter 4, not all of it, but most of chapter 4, because I'm assuming you know how to add vectors and you know how to take dot products. So hopefully that assumption's good. Okay, and now it's 2:45, so let me stop the share. And let me stop the recording.